SwayamPrabha. Digital India. Educated India.
Hello. Today I'll review the fundamental laws of fluid mechanics and heat transfer in brief. Content of the lecture are: under review of fundamental laws, I'll discuss Reynolds transport theorem and thus conservation of mass, conservation of momentum, both linear and angular momentum, conservation of energy, and then compressible flow relations, efficiencies of turbomachines. The basic physical laws of fluid mechanics and thermodynamics are: conservation of mass leading to continuity equation, conservation of momentum leading to momentum equations, conservation of energy giving rise to the first law of thermodynamics, and steady flow energy equations, and the second law of thermodynamics telling us the feasibility of the process. All these fundamental laws has been derived following control volume analysis. Thus, the control volume analysis is the tool for analyzing fluid flow behavior in space and time through these fundamental laws, that is, conservation of mass, momentum, and energy. Now, the Reynolds transport theorem applied to an arbitrary control volume can be expressed as d phi by dt for the system is equal to volume integral of phi plus surface integral of phi. Here small phi stands for specific property and capital phi is for the total property. And omega represents the volume, rho is the density, v is the velocity, and eta bar is the normal unit vector. So this equation can be stated as rate of change of phi in the system is equal to rate of change of specific property within the control volume plus net rate of efflux of phi across the surface. I have stated this as the instantaneous rate of change of phi in the system is equal to the sum of the time rate of change of property within the control volume plus net rate of efflux of property small phi across the control surface. I have discussed here the application of Reynolds transport theorem. Let's consider the conservation of mass. So for the conservation of mass, I can write for a system dm dt is equal to 0. That means mass cannot be created nor it can be destroyed. This leads to del t of volume integral rho into d omega plus surface integral rho v dot eta into dA is equal to 0. For the steady system, d rho dt is equal to 0. Then what I'll have, so this part goes to 0. So then I'll have surface integral of rho v dot eta into dA is equal to 0, which leads to the equations. If I consider that number of discrete areas through which the mass enters the control volume and also leaves the control volume, then I can write sigma of rho I AI into VI out is equal to sigma rho I into AI into VI in. That means mass flow through the different inputs balance each other. This can be stated as, for a steady system, the mass flow entering and leaving the control volume must exactly balance each other. Let us consider now the conservation of momentum. Now, the principle of conservation momentum as applied to a control volume is usually referred to as momentum theorem. Now, you would consider linear momentum and the angular momentum. With respect to the linear momentum, applying the Reynolds transport theorem, for the linear momentum to a control volume which is fixed in space, I can write that force on the control volume sigma F is equal to del T of volume integral of rho v into d omega is equal to surface integral of momentum flux out of the control volume, which can be written as sigma mi into vi out minus sigma mi into vi in. And this can be stated in words as the above equation states that the net force on a fixed control volume equals the rate of change of momentum within the control volume plus net momentum flux out of the control volume. For a steady system, this rate of change of momentum within the control volume would be 0. That means force on the control volume would be equal to momentum flux out of the control volume. Now I'll apply Reynolds transport theorem for angular momentum. Prior to that, let me define the angular momentum. So I have defined here the angular momentum of a fluid element of mass dm with respect to a point capital O is given by phi into integral of r cross v into dm, where r being the position vector of the fluid element with respect to a certain coordinate systems, and v being the velocity vector of the fluid element. So, angular momentum per unit mass, which is the specific property, small phi can be written as d capital phi by dm, that's equal to r cross v. So using transport theorem for a fixed control volume, I can write sigma m, where sigma m being the sum of all moments of discrete elements of mass with respect to O, that is the fixed point with respect to the origin, with respect to the coordinate system. So sigma m represents the total torque on the control volume, and this sigma m would be equal to del T of volume integral rho r cross v into d omega plus surface integral of rho r cross v dot eta into dA. So first term represents the momentum of the total volume, and the next one momentum flux out of the control volume. The above equation states that the torque on a fixed control volume is equal to the rate of change of momentum within the control volume plus net momentum flux out of the control volume. Now, if we consider the one-dimensional inlet and outlets and the system is steady, then we can write torque is equal to net momentum flux out of the control volume. That means this would be equal to sigma r cross v out into m dot out minus sigma r cross v into m dot in. Energy equation can be derived by applying Reynolds transport theorem, leading to the first law of thermodynamics, which is nothing but the conservation of energy. Thus, the energy equation can be written as Q dot minus W dot S minus W dot V is equal to del T of volume integral rho U V squared by 2 plus G into Z into d omega plus surface integral of rho into H plus V squared by 2 plus G into Z into V dot eta into dA, where Q dot is the heat added to the system, W dot S is the shaft work, and W dot V is the work due to the viscous effect. So the first term in this equation represents the energy of the control volume, and this is the energy flux out of the control volume because of the flow. Under the assumption of steady state and one-dimensional system, the above equation can be written as W dot. The above equation can be written as Q dot minus W dot S minus W dot V is equal to sigma H plus V squared by 2 plus G into Z into M dot out minus sigma H plus V squared by 2 plus G into Z into M dot in. This is known as steady flow energy equation. You are all aware of this. I have discussed here in brief the compressible flow relationships for perfect gases. The Mach number of a flow is defined as the local velocity divided by speed of sound. So it can be written as M is equal to C by A, where C is the local speed of flow and A is the sonic speed. And this can be further stated as C by root over gamma T. Considering the gas as perfect, the E is the sonic speed is equal to root over gamma T. Now, another very important point I like to remind you that whenever the Mach number in a flow exceeds about 0.3, the flow becomes compressible and the fluid density can no longer be considered as constant. What I like to tell you that suppose air is a compressible medium, but if the air speed is less than of Mach number 0.3, then air can be treated as incompressible media. So furthermore, high power turbomachinery requires high flow rate and high blade speeds, which invariably leads to compressibility. So for a compressors or turbine of high power and speed, the flow must be treated as compressible. Let us now start from the definition of stagnation enthalpy. So stagnation enthalpy H0 is defined as H plus half into C squared being the local flow velocity. Thus Cp into T0 is equal to Cp into T plus C squared by 2. And if I now use the definition of Mach number, which is further simplified as Cp into T plus m squared gamma RT by 2. Now using a perfect gas relation, gamma R can be written as gamma minus 1 into Cp. Thus substitutes the value of gamma by R here, and I can simplify it as T0 by T is equal to 1 plus gamma minus 1 by 2m squared. So this is a very important relation that tells you the ratio of stagnation to static temperature with respect to the Mach number. And you realize here that ratio between the stagnation and static temperature is related to Mach number squared. So as Mach number increases, this total temperature will increase the square of that. Now, after that, I'll try to establish a relation between the ratio of stagnation pressure to the static pressure. To do that, let me first define what is called stagnation pressure. Stagnation pressure in a flow is defined as the static pressure that is measured if the flow is isentropically brought to rest. Now using the Gibbs equation from second law of thermodynamics, T into ds is equal to dH minus 1 by rho into dP. Now if the flow is brought to rest isentropically, then I can write ds is equal to 0. Thus the above equation becomes dH is equal to 1 by rho into dP, that is equal to dP by P into RT using the ideal gas equation, which can be written as dP by P is equal to Cp by R dt by T. Further is equal to dt by T gamma into gamma minus 1. Now one can integrate this equation between static and stagnation conditions. And after integration, we will get the following relation P0 by P to T0 by T to the power gamma by gamma minus 1. So this is a relation between total pressure and total temperature from the static quantity in the. So now again I have already proved T0 by T is equal to 1 plus gamma minus 1 by 2m squared. Thus I can write P0 by P is equal to T0 by T to the power gamma by gamma minus 1 is equal to, within the bracket, 1 plus gamma minus 1 by T m square gamma divided by gamma minus 1. Now using the ideal gas relation, I can correlate rho 0 by rho with respect to T0 by T and thus Mach number with respect to Mach number. So I can write rho 0 by rho is equal to 1 plus gamma minus 2 by 2 m squared to the power 1 by gamma minus 1. So this is a very important relation which will be used in turbomachinery dealing with the compressible flow. Similarly, integrating along a streamline between two arbitrary points denoted by 1 and 2, I can say P02 by P01 is equal to T02 by T01 to the power gamma by gamma minus 1, and rho 02 by rho 01 is equal to T02 by T01 to the power 1 by gamma minus 1. Now if there is no energy added to the system, then T0 must be constant, which leads to P02 is equal to P01. It is further worthwhile to state that one of the most important relationships for turbomachinery with compressible flow is the non-dimensional mass flow rate, which sometimes refers to as capacity. Now I'll discuss later, I'll prove what is the expression for capacity. For the time, the expression is m dot root over Cp into T0. A is the representative area divided by P0. This capacity can be expressed in terms of Mach number, and I have given the relations. Now, please note that I'll discuss soon about the stationary and the relative frame of reference. Now, suppose I like to tell you for a turbomachinery, particularly the impeller rotates with an axis. So when you describe the flow field with respect to the impeller, we prefer to describe the flow field in relative frame of reference. Now, why I told absolute and relative frame of reference here? If we go to the next page, you will understand. Now note that when you express the quantity, total quantity, with respect to the relative frame of reference, then also the P0 by P0R is the total pressure in relative frame of reference, P0R by P T0R divided by T, and rho 0R divided by rho, and m dot root over Cp into T0R by A into P0R. So ratio of total quantity by static quantity in relative frame of reference and the capacity expressed in relative frame of reference can be expressed as a function of relative Mach number. So I have written an F of MR. Now here I have given a graphical representations of how the relation of total quantity and static quantity, they can be related in a graphical form. Suppose 1 is the static condition, 0,1 refers to a total condition. So this is 0,1 R, and this is 0,1 for stationary frame of reference. So for stationary frame of reference, total condition is denoted by 0,1, and relative frame of reference it is denoted by 0,1 REL. Now you can understand the relative total temperature and static temperature, the difference between this is nothing but W squared by twice Cp. W squared is the relative velocity. Similarly, the difference between total condition and the static condition in stationary frame of reference can be related with C squared by twice Cp. This is a very good representation. Hello. Today I'll review the fundamental laws of fluid mechanics and heat transfer in brief. Content of the lecture are: under review of fundamental laws, I'll discuss Reynolds transpose theorem and thus conservation of mass, conservation of momentum, both linear and angular momentum, conservation of energy, and then compressible flow relations, efficiencies of turbomachines. The basic physical laws of fluid mechanics and thermodynamics are: conservation of mass leading to continuity equation, conservation of momentum leading to momentum equations, conservation of energy giving rise to the first law of thermodynamics, and steady flow energy equations, and the second law of thermodynamics telling us the feasibility of the process. All these fundamental laws has been derived following control volume analysis. Thus, the control volume analysis is the tool for analyzing fluid flow behavior in space and time through these fundamental laws, that is, conservation of mass, momentum, and energy. Now, the Reynolds transport theorem applied to an arbitrary control volume can be expressed as d phi by dt for the system is equal to volume integral of phi plus surface integral of phi. Here small phi stands for specific property and capital phi is for the total property. And omega represents the volume, rho is the density, v is the velocity, and eta bar is the normal unit vector. So this equation can be stated as rate of change of phi in the system is equal to rate of change of specific property within the control volume plus net rate of efflux of phi across the surface. I have stated this as the instantaneous rate of change of phi in the system is equal to the sum of the time rate of change of property within the control volume plus net rate of efflux of property small phi across the control surface. I have discussed here the application of Reynolds transport theorem. Let's consider the conservation of mass. So for the conservation of mass, I can write for a system dm dt is equal to 0. That means mass cannot be created nor it can be destroyed. This leads to del T of volume integral rho into d omega plus surface integral rho v dot eta into dA is equal to 0. For the steady system, d rho dt is equal to 0. Then what I'll have, so this part goes to 0. So then I'll have surface integral of rho